A balloon will serve as the rocket's propulsion system by expelling air. A long string will act as the guide rail for the balloon rocket's trajectory. A straw will be taped to the balloon, allowing it to slide along the string. Tape is required to securely attach the straw to the balloon. Begin by carefully threading the string through the center of the straw. Ensure the string passes completely through, exiting the opposite end of the straw. Once threaded, pull the string taut. Maintain a straight line with the string, avoiding any kinks or bends. A straight and taut string is crucial for the rocket's optimal performance and trajectory. The demonstration focuses on securely tying a string between two fixed points. Suitable fixed points include stable objects like chairs or wall fixtures. Begin by selecting a strong and appropriate type of string or cord. Attach the string to the first fixed point using a reliable knot, such as a taut line hitch or a figure-8 loop. Stretch the string tightly across to the second fixed point, ensuring minimal slack. Secure the string to the second point with a similar strong knot, maintaining the tension. Begin by carefully inflating the balloon with air. Ensure the balloon is filled to the desired size and shape. Do not tie the balloon's opening after inflation. Hold the opening tightly to prevent air from escaping. Begin by inflating the balloon to the desired size. Carefully position the straw along the side of the inflated balloon. Use tape to securely fasten the balloon to the straw. Ensure the tape does not obstruct the opening of the straw. The initial setup involves preparing a balloon rocket for launch. The balloon's opening must be oriented backward. This backward orientation is crucial for propulsion. Air will be expelled from the balloon in this direction. The escaping air generates thrust, propelling the rocket forward. Proper setup ensures efficient conversion of air pressure into forward motion. A balloon rocket launch demonstrates principles of propulsion. The launch is initiated by releasing the balloon opening. Releasing the opening allows compressed air to escape rapidly. The escaping air generates thrust in the opposite direction. This thrust propels the balloon forward along the string, simulating rocket motion. A balloon rocket demonstrates principles of propulsion through air pressure. The inflated balloon contains compressed air, storing potential energy. Releasing the balloon's opening allows the compressed air to escape rapidly. As the air rushes out, it generates thrust in the opposite direction. This thrust propels the balloon forward along the string, creating motion. The speed and trajectory of the balloon rocket are influenced by air pressure and friction. Air is expelled from the balloon's opening. The escaping air generates a force in the opposite direction. This opposing force is known as thrust. Thrust propels the balloon forward. The balloon moves until the air supply is exhausted. A balloon is inflated and attached to a string. Air is released from the balloon's nozzle. The escaping air creates a force in the opposite direction. This force propels the balloon forward along the string. The balloon continues moving until the air is depleted, demonstrating propulsion. Newton's third law states that for every action, there is an equal and opposite reaction. This means that when one object exerts a force on another, the second object exerts an equal force back on the first, but in the opposite direction. In a balloon rocket, the action is the balloon expelling air. The reaction is the air pushing back on the balloon, propelling it forward. Newton's third law describes the relationship between action and reaction forces. The action is the air expelled backward from the balloon. The reaction is the balloon moving forward. This demonstrates that for every action, there is an equal and opposite reaction. Air pressure is the force exerted by the weight of air above a given point. In a balloon, air molecules are constantly moving and colliding with the balloon's inner walls. This constant collision creates an internal air pressure within the balloon. When the balloon is inflated, the air pressure inside becomes greater than the air pressure outside. Opening the balloon creates an escape route for the higher pressure air inside. Consequently, air rushes out of the balloon to equalize the pressure with the surrounding environment. A balloon rocket's movement is driven by the difference in air pressure. The air pressure inside the inflated balloon is higher than the external air pressure. When the balloon's nozzle is released, high-pressure air rushes out. This expulsion of air creates thrust, propelling the balloon in the opposite direction. A balloon is propelled forward by the force of escaping air. As air rushes out of the balloon's nozzle, it exerts a force in the opposite direction. This force is a direct application of Newton's third law of motion. For every action, there is an equal and opposite reaction. The escaping air pushes against the surrounding air, creating a reactive force on the balloon. This reactive force propels the balloon forward, demonstrating the principle of action and reaction. The magnitude of the forward force is directly related to the mass and velocity of the escaping air. The balloon rocket's trajectory is determined by the thrust generated from the escaping air. Air pressure inside the balloon propels it forward along the string. The rocket's speed is affected by the balloon's initial air volume and the rate of air expulsion. Friction between the string and the balloon influences the rocket's speed and distance. The angle and tension of the string also play a role in the rocket's overall trajectory and performance. Experimenting with different balloon sizes can reveal how size affects rocket performance. Varying balloon size changes the amount of air available for propulsion. Larger balloons store more air, potentially increasing thrust duration. Smaller balloons provide less air, possibly resulting in shorter but more intense thrust. Observing distance traveled and speed will demonstrate the impact of balloon size on the rocket's flight. The experiment involves comparing flight distance and speed using balloon rockets. Different size balloons will be used to power the rockets. The size of the balloon affects the amount of air available for propulsion. Larger balloons will likely provide more thrust, potentially increasing distance and speed. The experiment visually demonstrates the relationship between balloon size and rocket performance. String tension significantly impacts a rocket's stability and speed. Increased string tension generally leads to a straighter flight path. A tighter string reduces wobble and deviation during launch. This enhanced stability allows for a more direct transfer of force. Consequently, the rocket achieves greater speed and distance. The straw serves as a crucial component in a balloon rocket setup. It is affixed to the balloon, typically with tape, along its length. The straw is threaded onto a string, which acts as a guide rail. As the balloon deflates, the escaping air propels it forward. The straw ensures that the thrust is directed along the string. This alignment prevents erratic movements and maintains a straight trajectory. Aerodynamic drag is a force that opposes the motion of an object through the air. It significantly affects a rocket's speed as it moves through the atmosphere. Air resistance, a component of aerodynamic drag, slows the rocket down. The magnitude of the drag force increases with the rocket's speed. Reducing aerodynamic drag is crucial for achieving higher rocket velocities. An inflated balloon stores potential energy due to the compressed air inside. When the balloon's nozzle is opened, the compressed air is released. The escaping air exerts a force, propelling the balloon forward. This movement transforms the stored potential energy into kinetic energy. The balloon's motion demonstrates the conversion of potential energy into kinetic energy. The balloon rocket experiment involves repeated launches to demonstrate reliability. Each successful launch reinforces the consistency of the underlying physical principles. Multiple trials help confirm the predictable nature of the rocket's propulsion. Consistent results across launches validate the experimental setup and methodology. Observing several launches enhances understanding of the rocket's trajectory and performance. The repetition serves as a visual confirmation of the experiment's success and repeatability. Address potential problems that may arise during the balloon activity. One potential issue is the balloon detaching from its attachment point. Solutions should be prepared in advance to quickly resecure the balloon. Another problem could be the string sagging or losing tension. Consider methods to maintain string tension, such as using a lighter string. Having backup materials ensures quick fixes for common balloon-related issues. Further exploration of related experiments is encouraged. Viewers should be prompted to formulate additional questions. Focus should be maintained on air pressure concepts. Inquiries into principles of motion are also valuable. Continued investigation promotes deeper understanding.